Our presentation is over Lake Erie water quality due to runoff from surrounding watersheds by Monica Peebles,
Taylor Tweed, Sarah Fleckenstein,
and Megan Modisett.
To explore the ecological environmental change in Lake Erie, we decided to look at how runoff from nearby farms affects the water quality of the rivers and lakes that feed into Lake Erie. There is nutrient mobility in soil due to rain and soil runoff. This runoff leaks into rivers and lakes and causes changes to the ecological environment, especially watersheds that flow into Lake Erie. To explore this idea, we looked at literature from Interacting Effects of Climate Change and Agricultural BMPs on Nutrient Runoff Entering Lake Erie, Phosphorus Losses from Monitored Fields with Conservation Practices in the Lake Erie Basin, USA, and finally, Sediment-Assisted Nutrient Transfer from a small no-till tile-drained watershed in southwestern Ontario, Canada.
Interacting effects of climate change and agricultural BMPs on the nutrient runoff entering Lake Erie. This experiment was conducted to evaluate the effectiveness of BMP better management practices in a current climate, as well as comparing the most effective BMPs to the estimated climate within the next several years. This experiment was localized in the Lake Erie watershed and concentrated on runoff, including nitrate levels and sediment concentration. According to Carpenter et al. In 1998, the export of nutrients from agricultural watersheds and the resultants decline in water quality are widespread concern, potentially affecting drinking water supplies and recreational values as well as the ecosystem health. Runoff is very much increasing due to increasing temperatures. This is ultimately affecting our drinking water and the health of the ecosystem. There have been many studies done to reverse the amount of runoff that has been contaminating our water sources. These are known as best management practices. BMPs include the ideas such as no-till, planting cover crops, and planting shrubs surround the crop field. These BMPs are highly effective in a current climate, but the concept of climate change is not involved. Climate change has been proven to make these practices less effective by dramatically increasing the amount of surface runoff in the spring and water months due to higher temperatures and less freezing conditions. The increase in rain output due to the decreases in temperatures results in an increase in nutrient and sediment runoff. The surface runoff is likely to have greater effects on the water quality when compared to the precipitation. According to this article, Bosch et al. States, although changes in the amount, timing, and magnitude of precipitation and surface runoffs are likely to have the greatest effect on water quality, temperature change will affect the growing season and may alter the hydrolytic cycle via increasing of transevaporation. Bosch and his crew did an experiment that included 4 watersheds: the Raisin, the Maumee, the Grand, and Sandusky. The 4 watersheds that were studied in this experiment were used because they all empty into Lake Erie watershed, but are very different geographically. The Raisin, Maumee, Sandusky were dominated by agricultural land. The Grand was mostly forested, but did receive a significant amount of rainfall. The Maumee was the largest watershed in this experiment. This image represents the 4 watersheds that empty into Lake Erie. This helps visualize the location and size difference of the watersheds and could be contributing to the runoff of the Lake Erie watershed. This experiment ran from 1995 to 2005. During these years, there were 3 sections of experimentation. These included a 3-year model of a spin-up from 1995 to 1997, of 4 years of calibration from 1998 to 2001, and 4 years of confirmation from 2002 to 2005. Calibration and confirmation included steam flow discharge, sediment loads, and nutrient loads. These were observed daily by the USGS gauge station near the water mouth of each watershed. These sediment and nitrate loads from the watersheds were observed daily from the National Center of Water Quality Research. Model calibration and confirmation results showed that the experimental testing was reasonable and warranted, according to Bosch et al. 2011. Many previous experiments, report, and predictions were used to calibrate accurate climate change for the future. scenarios were developed and based on the projections made by Howitt in 2010 for Western Lake Erie region. These projections were repetitive at high and low greenhouse gas emission scenarios. The climate projections were constructed based on the results of three atmosphere-ocean general circulation models. An experiment was then designed to stimulate climate change and measure the water quality of runoff. The parameters from TMPINC were used to increase the observed daily minimum and maximum temperatures by the desired number of degrees that were selected for the month of each year. Precipitation was also measured. The daily precipitation values for the calibration and confirmation period were averaged and used as a control. Experimental conditions were measured and averaged for the 1970 to 2009. Results of this experiment include, with the climate change and the runoff increased overall only 1 to 4% with the use of better management practices. The sediment yield increased from 6 to 18%. The nutrient yield increased 6 to 8%, and the nitrate yield increased 16 to 18% without better management practices and a climate change. The precipitation only increased 6%. When considering climate change without the use of BMP, the watershed sediment yield increased by 6 to 18% with a mean of 13% under the moderate climate scenarios, but it changed substantially more under the pronounced climate change scenarios, ranging from 20% to 40% across the four watersheds with an average of a 39% increase. This experiment ultimately concluded that BPMs are highly effective to reduce the runoff at current climates, not when considering a climate change. Although the precipitation's amount increased due to climate change, the total runoff remains relatively low. BMPs are effective at limiting runoff without climate change being considered. Bosch states, our model suggests that under higher implementation rates, BMPs should be able to offset the expected increase in climate. This tells us that BMPs are not 100% effective, but are very significant in reducing the amount of runoff. Maumee, Sandusky, Grand, and Raisin watersheds overall responded to this experiment differently. This is due to the geological characteristics. Each of the four watersheds responded differently to the BMPs due to geological characteristics as well. Phase in the paper is, this has implication for public policy as new initiatives to create for farmers to adapt BMPs, and tighter regulations are placed on how the land can be used. In total, these BMPs decrease the speed of sedimentation load in surface runoff. Although BMPs are highly effective limiting the amount of runoff and sediment that decrease the water quality in Lake Erie, they are not applicable for farmers. At high levels of BMP that must be used for farmers in order to completely eliminate runoff is rather expensive and time-consuming. The process includes hiring an evaluator to determine the more effective BMP to use due to geological characteristics, crop land management, and the cost of. Another important discovery from this experiment was the fact that BMP implementation is very effective during the current climate. But because the current climate is changing, it is very hard to estimate how effective BMPs will be after several years. Understanding better management practices is important to keep in mind to maintain higher quality of water, but BMPs do not provide a high enough level of improvement when considering climate change.
This study correlates to what we would like to focus on because both the article and our study aim to evaluate best management practices. This study focused on the impact of climate on BMPs, and we would like to investigate the impact of location on BMPs. The most important fact we will be taking home from this study is that BMPs are not an ultimate solution. However, this article will help us design a proposal since it recognizes the fact that geology and climate of the watershed will impact the BMP. That being said, in our study, we will need to Make sure we try and control these variables to the best of our ability when we decide which locations along the Maumee River we will be testing.
Sediment-assisted nutrient transfer from a small no-till tile-drained watershed in southwestern Ontario, Canada. From this research project it is possible that Lake Erie's current eutrophic state is due to increased nutrient loading stemming from recent changes in land use. Ontario reported increases in no-till operations and decreased fertilizer use over the last decade. Research suggests that no-till prevents fertilizer-based nutrients from being mixed into soils, allowing for rapid nutrient transport and surface runoff, with tile drains linked to the nutrient-laden runoff directly into the draining systems. Many farmers have adopted no-till operations over the last several decades as a way to address and mitigate land degradation issues. Nutrient transport pathways can be inferred through the relationship between suspended sediment flux and nutrient loading. Current research suggests that a connection between the surface water nutrient loading and fine-grained soil fraction. This study proposes that the quantity and quality of suspended sediment yields in agriculture settings contribute to nutrient transfer from surface runoff, and that agriculture practices such as no-till and tile drains have an impact on the hydrological and the sediment and nutrient loading responses to rainfall inputs. The project that we are working on focuses on the reentrophication and how best management practices play a role into it. This article concentrates on the no-till tile drain farms directly influence the watershed and lead into Lake Erie, which directly correlates to the project that we are working on with determining where best management practices work best. For the first part of the methods, it's the study site. The water quantity and quality were measured in a small tributary draining into the Rondeau Bay in Lake Erie. The study ranged from May to October 2013. The length of the watershed was about 2.5 kilometers in length and drained into a sub-watershed that was approximately 3.8 kilometers squared. The soil in this area was considered a silty clay loam. This soil is characterized as poorly drained due to, in part, to the fine textured nature of the region's surfical deposits. The fields that were cropped around it were cropped with corn, soybeans, and hay during the study. Seeding occurred in early May, and the crops were harvested throughout October. The second part of the methods refers to the data collection. The rainfall was the primary weather factor that controlled runoff generation in the field study during the study period. Rainfall and temperature was recorded with Davis Instruments Vantage Pro 2 Plus, and a tipping buckets were located nearby. Each of these buckets were equivalent to 0.3 millimeters of moisture, and temperature was monitored in 15-minute intervals. The stream level is monitored with pressure transducers, and there's 3 stations established, and gauging and water collection was done weekly. The water samples were then analyzed for suspended sediments and particle sizes, as well as the total phosphorus, orthophosphate, and total nitrogen content. Nutrient spectrometry assessments were conducted on collecting water samples with a HACHDR 2010 spectrometer. Map of the location of the watershed that we are looking at for this research article. The monitoring stations were established approximately 10 to 15 meters upflow at each of the following roads. Talbot Eds in front that intersected the monitoring reach from which the streams were accessed for gauging sample collection. The monitoring stations can be noted on the graph by looking at the stars. This table demonstrates the rainfall event summary. It also includes soil moisture conditions and the flow generated at the monitoring stations. Each event summary includes a rainfall event, as well as the rainfall, the 24-hour rainfall, the 5-day ascent rainfall, and the flow at each of the stations during these days. We should pay special attention to July 19th, the greatest amount of rainfall, as well as October 6th, one of the days with the least amount of rainfall. In this figure, figure A, demonstrates the suspended sediment concentration before the big rainfall that was mentioned on July 19th, after July 19th, and then a while later on September 12th. As you can tell, there's not much difference in the suspended sediment concentration from either of these three dates by looking at figure A. By figure B, demonstrates the fine particle grain particles before the rainfall on July 19th, after July 19th, and then a while later on September 12th. You can tell that before July 19th, the percent of particles range quite a bit, from 30 to about 70%. But after the rainfall on July 19th, there is a significant increase in the percent of fine-grained particles. On September 12th, a day of no rainfall, particle percentages are back down to the levels of before the rainfall that occurred on July 19th. In this figure, we notice a clockwise hysteresis pattern exhibited on October 6th at the Talbot station. The clockwise loop was apparent at Talbot, Eds, and Front stations during this rainfall event. During monitoring rainfall events, the highest suspended sediment concentrations did not coincide with the event hydrograph peak, and the clockwise hysteresis loop was observed, which suggested that erodible particles were entrained by the first flush of water. A clockwise loop indicated that contributing sediment sources are from the channel bed banks and other quick access sources such as tile drains from fields. The clockwise pattern further indicates that contributing sources were exhausted over the course of rainfall event, as evidenced by the reduction of the suspended sediment concentrations prior to the discharge peak. By taking this knowledge and applying it to the last graph, we can explain why the suspended sediment concentration showed no difference between before the July 19th event and after the event, then nearly 2 months later on September 12th on a no rainfall day. We can assume that there is no significant difference in that figure due to the concentrations of the suspended sediments 24 hours after the rainfall returning to levels equal to that before the rainfall, as explained by this clockwise hysteresis. In conclusion, this study evaluated the hydrological, sedimentological, and nutrient loading response to summer rainfall inputs in a small agricultural watershed in southern Ontario. The research demonstrated that runoff generation caused by rainfall events leads to sediment and nutrient mobilization. Tile drains connecting the fields directly to the draining system and became the pathway for the sediment and nutrient transfer. Water samples were analyzed for phosphorus, orthophosphate, and nitrogen content, and those all exceeded the Ontario Provincial Water Quality Guidelines. A positive relationship between the suspended sediment concentration, phosphorus, and orthophosphate confirmed that phosphorus loading was sediment assisted. Therefore, high nutrient loads occurred in the monitoring streams despite land management's efforts to prevent sediment and nutrient transfers through their no-till practices.
This article will be beneficial in composing our proposal because this study confirms that there is nutrient mobility in agricultural soil and that phosphorus loading is sediment assisted. This information will fit nicely into our introduction when we discuss the re-eutrophication of Lake Erie with regards to phosphorus, which is the main nutrient our study will focus on. We can use this source to cite the fact that phosphorus loading is indeed sediment assisted and that BMPs can manipulate the amount of runoff. This point will allow us to argue why our research idea is important and relevant.
next article we will discuss is phosphorus losses from monitored fields with conservation practices in the Lake Erie Basin, USA. This article was selected for this assignment because it ties in well with what we would like to investigate, which is agricultural best management practice in the Lake Erie watershed. Lake Erie is the southernmost of the 5 Great Lakes and also the most biologically active. In recent years, harmful and nuisance algal blooms have become more prevalent, with the predominant contributing factor being the influx of soluble phosphorus floating into the lake. To try and circumvent this problem, the United States government passes a farm bill every 5 years. The farm bill sets aside money for agricultural conservation programs such as no-tillage, grassed waterways, underground outlets, water and sediment control basins, conservation crop rotation, and residue and tillage management. Conservation crop rotation has been the most highly promoted BMP recently, since it is believed that introducing more crops into the rotation will improve overall soil quality and that the healthier soil will decrease sediment, nitrogen, and phosphorus losses from fields. In 2008, this bill was passed for $57.7 million. This study was conducted to assess the impact of Farm Bill conservation practices on soluble phosphorus and total phosphorus losses from 4 fields that were monitored between 2004 and 2013. In this study, no-tillage, conservation crop rotation, grassed waterways, and blind inlets will be looked at and evaluated specifically for the St. Joseph River. What we have here is a graphic representing all of the Maumee watershed, and as you can see, the St. Joseph River is a tributary branching off of the Maumee River in northwestern Ohio and northeastern Indiana. It drains mostly rural farming land, and as a result, some of the primary Farm Bill conservation practices have already been adopted in this watershed. In order to collect data for this study, 4 fields in the St. Joseph River watershed were monitored for both surface runoff and tile discharge. These fields are privately owned, so the primary selection criteria were a portion of the area in a single management zone draining surface runoff to a single point, and that the landowner be willing to allow access for a long-term monitoring. Fields 1 and 2 were owned by a farmer and managed with a corn and soybean crop rotation, and no-tillage had been in practice since 1990. Field 1 continued no-tillage throughout the duration of the study, while Field 2 switched to rotational tillage throughout the duration of the study. Fields 3 and 4 were a pair of closed depressions or potholes, which was also farmer-owned and cropped using conservation crop rotation. Both Fields 3 and 4 used tile risers and a blind inlet with tilling between each crop. Generally, the tile riser drained one field, while the blind inlet drained the other. The blind inlets described in this study are a device the researchers developed. They were plastic 15-centimeter diameter pipes that extended about 1 meter above the soil, and they had about 2-centimeter diameter holes to drain water while retaining large debris. Blind inlets in comparison to tile risers are novel because they allow farmers to perform field operations over the drainable area, unlike tile risers. In order to physically collect data, the following on this slide was treated as protocol. Surface runoff and tile discharge were monitored in all 4 fields. Discharge measurements were recorded every 10 minutes. Sample of surface runoff was collected every 30 minutes when present. Subsurface tile discharge was recorded every 2 minutes, and tile water samples were collected every 90 minutes. All water samples were refrigerated immediately upon collection and removed from auto samplers within 48 hours of collection. For sample analysis, all nutrient analyses were conducted using a ConeLab Aqua 20, which is an automated clinical chemistry analyzer. Soluble phosphorus was analyzed on vacuum-filtered acidified samples using EPA method 365-2, and total phosphorus was analyzed using EPA method 365-4 after mercuric sulfate digestion of the unfiltered samples. Both EPA methods were a method commonly used to test for specified species of phosphorus in drinking, surface, and saline waters. To analyze the data, mean concentrations for surface runoff were calculated. By doing so, each sample is weighted by both time and the flow that accompanied it.
The flow-weighted mean concentration represents the total load for the time period divided by the total discharge for the time period. From here, medians were also compared using JMP computer program, which is with a significance level of 0.10. The loads given in this state represent the growing season, which is from April 1st to November 15th. So here we have our first table, and this table represents the crops and conservation practices in each field and the number of surface runoff events in the 4 fields monitored in the St. Joseph River watershed. So as you can see in this table, N is for no-till, G is for grassed waterway, C is for conservation crop rotation, and B is for blind inlet. And reading off this table, Field 1 was crop using continuous no-tillage, which is planting directly into crop residues from previous crop, while Field 2 was converted from continuous no-tillage to rotational tillage, which is just tilling prior to planting corn. Field 3 and Field 4 were tilled between each crop. In Fields 1 and 2, they were cropped using a corn and soybean rotation, while Fields 3 and 4 were cropped using a corn, soybean, wheat, and oat rotation, which is more commonly referred to as conservational crop rotation. Imperial gullies developed in Fields 1 during the winter of 05 and 06, and in Field 2 in the winter of 09 and 10. Thus, grassed waterways were established in these fields in 06 and 10, respectively. Following along with more results, these graphs show the median soluble phosphorus and total phosphorus concentrations in surface runoff from each type of best management practice implemented in this study. So this graphic is neat in that it allows one to compare side by side the different conservation practices utilized in each of the 4 fields. In tillage practices, it can be observed that no-tilling resulted in greater soluble phosphorus concentrations compared to rotational tillage, and that it had relatively the same impact on total phosphorus concentration. In the crop rotation practices, it can be observed that conservation crop rotation is clearly the better crop rotation choice, since it reduces both soluble phosphorus and total phosphorus concentrations. For the grassed waterway practice, there appears to be no conservative benefits as the soluble phosphorus concentration increased in comparison to the control, and there is no great difference in total phosphorus concentrations. Finally, it appears that the blind inlet practice holds some promise as it decreased the soluble phosphorus concentration in comparison to the tile riser that held the total phosphorus concentration relatively the same. So in conclusion for this study, most of the conservation practices applied to fields were developed in order to decrease sediment losses from farm fields. And although sediment losses were not investigated in this paper, the common knowledge at the time was that if sediment losses were reduced, phosphorus losses would be reduced at the same time as well. And this mindset was disproven in this study because, as just discussed in the previous slides, no tillage decreased surface runoff total phosphorus loads compared to rotational tillage, but nearly doubled soluble phosphorus, which, if you recall, that's usually the main causative agent of these algal blooms. And soluble phosphorus and total phosphorus were less in surface runoff and tile discharge from conservation crop rotation compared to corn and soybean rotation, so that kind of proves there that conservation crop rotation kind of holds some promise. Grass waterways decrease soluble phosphorus and total phosphorus in surface runoff, and blind inlets decrease soluble and total phosphorus loads in surface runoff compared to tile risers. There was a 17 and 58% decrease in soluble phosphorus and total phosphorus loads respectively for the treated areas. From these results, these BMPs could be used to reach the target reduction in total phosphorus content, but since the impact on soluble phosphorus was so low, it does not appear that the adoption of these practices will help in reaching the target soluble phosphorus reduction. Greater adoption of these practices, in addition to new strategies, will need to be adopted in order to achieve the desired water quality goals of 41% decrease in soluble phosphorus loading and 39% decrease in total phosphorus loading into Lake Erie. This again ties in with what we wish to research for our proposal idea, since we would like to expand upon the idea of best management practices and see if location has any impact on their effectivity, so investigating if they're better off being placed closer to where these rivers empty into Lake Erie, or if they're better off in the further out tributaries. As you can see, this article has some great ties with what we would like to research. Both the article and our research focuses on agricultural best management practices. However, the article focuses on which BMP is best at improving water quality, while we wish to assess if location of the best management practice impacts water quality. Likewise, this article study was done on the St. Joseph's River, a tributary of the Maumee River, while we would like to focus explicitly on the Maumee River itself. We hope that by understanding this study, we can apply some of the same analysis and gain a better understanding in how we can go about collecting data.
That concludes the discussion of the 3 articles that we chose for this assignment. And by looking at these articles, we were able to tell that tillage practices and best management practices had some benefits, but not to the extent that are desired or required to make a change. Overall, soil management practices help decrease the amount of runoff that finds its way into watersheds. However, the decrease isn't a significant amount, so other solutions still need to be found. These 3 articles will be beneficial in exploring the impact that location has on the effectiveness of BMP, which is what we're choosing to do our research project on. And after exploring these research articles, we decided to investigate the proximity of best management practices to Lake Erie on the Maumee River. References for the 3 articles that we used.